All right, everyone, welcome to the final X1 Robotics workshop for this year, Geometric Dimensioning and Tolerancing. So we'll have me and Matthew, who are your new X1 leads, as well as John is going to be leading us through some demos.
Yeah, so today basically we're going to be working through the basics here of exactly what GD&T is. We're going to go through the basics of the practice, some of the more advanced practices as well. And we're going to run through a demo, and then we're going to show you guys some additional resources. And so basically, just to define GD&T, it's a system for defining and communicating engineering tolerances on certain dimensions of a part. And it's made with three goals in mind, which are functionality, repeatability, and measurability.
So here's a couple of definitions, words that are used when referring to GD&T that are really useful to know. Engineering drawing, first up, is the technical drawing that communicates all the information necessary for manufacturing. So the key there is that there's more information than just dimensions, which is what we're going to talk about. It's all the information necessary to manufacture your part. So the dimension is the value itself that's associated with a certain feature. And a tolerance is the accepted deviation from that dimension. So how much you're allowed to be inaccurate, because it's impossible to manufacture anything perfectly. So datum is a really important term, which is the fixed reference or the starting point, which is usually where, like, a point that you're measuring from. And geometric control refers to the type of dimension control you're imposing. So it goes with a symbol or a notation. It's just a different term for what kind of dimension you're putting on it. Okay. So
yeah. So
you start out, Matthew.
Right. Yes. So basically, this is the sort of abridged version of a lot of some of the fundamental rules that need to be followed when doing this practice. Basically, we need to tolerance everything. And scaling and assumptions are not allowed, because I suppose those can be ambiguous to people who may be receiving the drawings. Also, as you may have learned just from basic SolidWorks, is don't over-define features, because it can be very confusing and redundant. And also, the dimensions to be chosen to reflect the function of a part. So for example, maybe if we need something with extreme precision, we can dimension it first so that error does not stack up on it.
So number 5, drawings shouldn't specify a manufacturing method. That's not really their job. That's up to whoever's going to be receiving it, unless it's absolutely necessary or it's very specific instructions. Drawings should be optimized for readability. That's just, to make everyone's lives easier. An angle is assumed to be 90 degrees unless specified. So that's a key one that you don't actually have to dimension. It's assumed to be 90 degrees if it looks 90 degrees. And then dimensions and tolerances only apply at the drawing level, not globally. So I think that refers to maybe if there's other parts in your whatever you're building, you don't continue things that are in one drawing onto another unless you actually write them again.
Cool. And then just to do a quick thought experiment, which of the following is dimensioned correctly? So these are all the same part. It's a little mounting bracket, I guess, if you will, with 4 holes in it. So if anyone would like to wager a guess of which of these is the correct one.
Any volunteers from the crowd? All right, if not, that's okay too.
I'll give it like a couple more seconds in case anyone feels brave. First one, cool. I'll give it just a couple more seconds just in case anyone else wants to say anything. But essentially, the correct answer is technically all of them are correct. So if you wouldn't mind clicking, Rebecca. Yeah. So this kind of comes down to the main point that Matthew brought up when he was reading the fundamental rules on the previous slide of functionality is one of the most important parts about how you do these drawings. So technically, all 3 are correct. Well, technically the first 2 are correct, and the third one is acceptable but not common practice. So the first one, right, each hole is being dimensioned explicitly from one of the edges, in this case, the bottom edge and the left edge. So this signifies that the function of this part, it is more important for those two sidewalls to fit into something else than it is for those holes to be like perfectly spaced away from one another. Versus if you look in the middle one and the right one, we care way more about the holes being 50 millimeters apart than we do, say, how far they are from the edge. So that's just to reiterate the kind of the important part about how you have to kind of consider what the function of your part is while you're making this drawing, because though they're pretty similar, the difference comes up in how the tolerance is, because on the left side, it's going to always be plus or minus 0.1 for each of those measurements from the wall, but the distance between the holes can be, say, plus or minus 0.2. Versus on the right two, the middle and the right one, the holes are always going to be plus or minus 0.1, even though you might end up in a situation where the topmost hole is, say, plus or minus or 0.2 away from the bottom edge. And then just to kind of give the last kind of qualification, the reason the right one isn't standard is because you usually want to take all of your measurements from a set reference frame. So that would be the bottom wall. It's kind of weird to like double back this way, even though it is okay, it's kind of frowned upon pretty harshly. So cool. Now we're going to get into a bit of the more complicated stuff that you can get into with GD&T. So obviously basic drawings are great, you know, the what we just talked about. They're great for rapid prototyping if you just need something done really quickly. But one of the main advantages of GD&T, especially advanced GD&T notation, is the fact that when you have large scale production, when you want to imply more control and kind of have better measurement techniques specified, you kind of have to use this more advanced GD&T method. And that all starts with the feature control frame. So that's the fancy name for the little box you see on the right side of the screen underneath I believe it's a poodle wagging its tail. And essentially the feature control frame, you know, has a couple important things on it. So if you wouldn't mind just clicking through these, Rebecca, as I go through them. So the first one is type of control. So this is specifically, you know, what kind of engineering control you're implying. So this symbol right here signifies position. So that would mean this feature control frame is specifically about the position of a feature, but there's a bunch of other ones. So there's ones, the next slide will show them, but there's ones about like, you know, how parallel this is. So another datum, how perpendicular it is, you know, how much we're removing. There's a bunch of different stuff like that. So that's the type of control. The next one is type of tolerancing. So, you know, by default in the last slide, you saw that we gave an X and Y dimension and then gave plus and minus tolerancing for both. That would imply that you technically have a square of 0.2 millimeters as your like acceptable tolerance, right? Because you have plus and minus in one direction and plus and minus in the other. So that would collectively be you know, an area of acceptability of a square that's 0.2 millimeters on either side. So type of tolerancing gives you this added feature where you can say, hey, well, instead of a square, as long as you're within a circle of X amount radius, then you're still okay. It's an acceptable part. That's what type of tolerancing is. Tolerance value is the number associated with that. So in this case, I'm saying, you know, I want to, as long as my feature is within a circle of 0.03 millimeters, I'm okay. And then the next one, which is size and tolerance modifiers. These are the optional ones. They're not shown, but they go right behind that number. That's a little bit like too complicated. We can get into it if we have a little bit extra time, but essentially there's like additional modifiers you can add as the engineer and as the like manufacturing engineer for this process. So for example, they'd revolve around like one example is, let's say you're trying to fit like a peg into a hole, like the previous part that we had just drawn out, and you wanted to specify a couple more things about like how the peg fits in the hole, that kind of stuff. There's additional symbols for that. And the last ones, which are the most important ones, are the reference datums. So these are what you're taking your measurement with respect to. So yeah, that's the feature control frame. We'll walk through an example on the next slide to hopefully clarify this a little bit more, but that's at least the basics of the feature control frame. So next slide, please. So yeah, so advanced GD&T, here are all, well, most of the symbols. There are a couple more, but these are the mainly used ones that I was talking about. So you can see at the top, you have, position, line profile, straightness, roundness, flatness, perpendicularity, all of these things. So that's that first part of the feature control frame that I was talking about, where you get to kind of specify what exactly you're asking the person to measure. And that's kind of an important sentence, because the whole point of GD&T, well, not whole point, but one of the main points of GD&T is making sure that the part that is made in the end works correctly. And it will only work correctly if we measure it the correct way. And GD&T is kind of how we as engineers get to say, okay, well, this is how I need you to measure it for it to be correct. And so these are, the symbols associated with that. At the bottom part of that box, you see there's MMC and LMC. That stands for maximum material and I think least material. Essentially, those are that additional modifiers that I said, that I mentioned, as well as projected tolerance, free state, and tangent plane. Those are all, those kind of additional things that you can specify that maybe I'll get back into if we have more time, but I think for right now we can skip. But essentially, that being said, let's walk through an example. So taking into consideration that that feature control frame at the bottom of it, if you wouldn't mind clicking next. So the first thing that we see is this tells us that we have two holes, right? Two holes, each of diameter 0.125 millimeters. Technically, there should be a tolerance associated with that, but we'll ignore that error for now, even though there should be a plus or minus, say, 0.005 or whatever at the end of that. But we'll go ahead and ignore that. Then the next one after that, we see the symbol used as position. So this tells us, if you click next, it's telling us that we want the position of these holes to fall under, or actually, I'm so sorry, if you wouldn't mind going back one, if it lets, yeah. So this tells us that we want a position of using a circular kind of area, right? That's the diameter symbol of 0.015. And to clarify that a little bit more, what that is saying is you want the central axis of your 0.125 millimeter holes, right? Those two that we're drilling, to fall into this circular area of acceptability with a diameter of 0.015. So I know that's kind of like a weird thing to say. Hopefully I said that all right. Feel free to ask me to clarify after we run through this example, because I know this is kind of going to be a lot of new information, but essentially that's what that is saying. It's saying each of those holes has to fall under that, or fall into that area of acceptability, rather than, on the previous slide where it was 2 plus or minus dimensions, which makes it a square area of acceptability. So hopefully that makes sense for that one. Then the next one, so A and B, those first two tell us that we want our XY position of our holes to be taken, with respect to our A and B datums, which are quite literally just, there will be a marking on the diagram that says hey, this is datum A, hey, this is datum B. And then when you measure it, it's just saying measure with respect to that. The last one, which is an optional one, is C. So this tells us that there's a third datum that we're taking our measurement with respect to. And in most cases, it implies it's perpendicularity of it. So let's say we had a 2D part, kind of like the previous one, where it's a mount and we have our holes in it. A and B would be the sides of the square, and C would be the top face, telling us that we want our part to be aligned in such a way that that central axis of our hole goes perpendicular to C, and then of course falls into that circular, or I guess cylindrical, since it's a 3D part, cylindrical area of acceptance with diameter 0.15. And then the last one, which is again is the optional one, is this MMC, which is maximum material condition. I looked it up real quick just to make sure I don't get it wrong. So MMC is maximum material condition, LMC least material condition. All that is essentially saying is we want the maximum amount of material remaining on our part. And since our part is a hole, that means we'd want a 0.14 peg to fit through it. How I got that number is you get 0.125, which is the original diameter, and then you add the your kind of tolerance diameter to it, and that tells us that, hey, that's like the maximum number that this should be able to fit, and that's that peg. Again, that's kind of the more complicated stuff, and I don't want to confuse y'all too much, so we can just kind of ignore MMC and LMC for now. They usually don't get used that often anyways. But yeah, I know that was a lot. Any questions about, you know, this feature control frame and roughly how this works? Hopefully the SolidWorks demo will also help, but you know, at anything I can try to help clear up at this time. All righty. Okay, I think we're good to move on then.
Yeah, so
There we go.
oh, wait, okay. Yeah, so SolidWorks again has a means of kind of working with GD&T and doing dimensioning. And it's simple and fast to implement. I've done it once or twice myself. It sometimes it automatically dimensions for you, but it's not I don't think it's the best practice. And yeah, there's a couple of annoying bugs to be expected. But you should always make sure that GD&T is optimized for function. This is kind of like we mentioned earlier, the 3 examples of the that 4-hole sheet of metal where we need to really design for purpose.
Yeah. So here's a couple just screenshots of what the tools look like when you're looking at them in SolidWorks. And this is once you've opened SolidWorks drawings. So this would probably happen after you've completely designed your part. You've made the full 3D model. You go in drawings, and then you have all of these different options for ways of making dimensions. And there is a tab for geometric tolerance, where you can look at different properties, and you can see it shows a lot of these same symbols that we're talking about. So it has options for you to insert those symbols into your drawing. And a quick note on this is that, remember, if there's anything that you want to edit directly on your diagram, you have to go to edit sheet format. And that allows you to change the title, revision, drawing number, etc. Basically, I've gotten in this a lot where, like, I'm trying to edit something and only edit it. You have to go to edit sheet format to actually like type things directly on it. So those are just quick tips of how to do this in SolidWorks drawings. We'll see John's demo of it in a second.
Cool. Yeah. If you wouldn't mind giving me share permission, I can go ahead and get this started.
I think you have permission.
Cool. Yep, I do.
All right.
Okay. So, all right. So you should be seeing SolidWorks. This is the part that we're going to be dimensioning. You can see it's a pretty simple bracket. We have this larger hole in the middle, these 4 smaller holes on the side, and this kind of intricate design, which I just kind of did to make it a little bit more complicated. I'm not quite sure what this would be used for, but essentially that's that. So now to start this off, we're going to go ahead and go over here and click Make Drawing from Part Assembly, or Part/Assembly rather. Now it's going to ask me how I want to format this. I'm just going to go ahead. SolidWorks has a bunch of default ones, and this will kind of really depend on, if you're working at like a company, it will depend on what the company practice is. Typically, you know, you could probably get away with like A landscape or A4 landscape, because those are, you know, like your printer papers. I'm just going to go with that for now, just to get something going. So you can see really quickly the edit sheet formatting. Any of this text down here, I will not be able to change unless I click edit sheet format. Then I'll be able to, you know, come down here, say drawing number should not be bracket. Drawing number will probably be like 001, and my title would probably be bracket, maybe bracket A. If I wanted to like sign my name as I drew it on this day and all that stuff, I'd also be able to change it here. But that's kind of a waste of time if we do that. So the first thing I'm going to do is I'm going to add in the model. So obviously, if I go to drawing, model view, I have my file open, so I have bracket, and then SolidWorks is going to let me add this in right away. In my case, since this bracket is drawn top down, I'm going to click the top view. These are all, you know, your views. You can pick isometric and all that stuff if you just going to do top one to keep it simple. And then I'll probably do just the bottom one because the right one doesn't really matter in this case. I'm also going to enable this right here. So all I do is click on this and click the hidden lines visibility. If you've taken 94, these are those pesky lines that they make you draw by hand, signifying that, you know, this hole goes all the way through and this hole goes all the way through here. And that's basically it. We have our drawing. If we want it to be nice to our parts manufacturer, maybe we add in another model view that's isometric and fully filled in. That could go here at the top corner, just so that they have like another reference of, oh, okay, cool, that's what that looks like. Don't really have to do that though, but it is nice if you have room on your drawing to include something like that. Now we're going to go to annotation, and this is where most of your time is going to be spent. This is where you're going to start you know, measuring everything, marking all that stuff. So the first thing I'm going to do is we'll go ahead and click Smart Dimension. Just normal Smart Dimension for now is okay if it lets me do it. Yep. We'll go ahead and take, say this is our datum 1. So we'll go here and we'll go up to here. This tells us that we have 20 millimeters as this distance. That's good for now. In this case, let's say the distance between the holes is more important, like we talked about. So I'll go ahead and do this. So now we have our compound tolerance right there. And then these two, if we don't measure them off, it's going to be implied that they're equivalent, which is okay in our case because they are. The next thing we'd need one from here to the center of here. So there's that one, as well as, you know, some of the other ones. So we'd need this total distance. And we'd need, you know, the distance from here to here. There's a couple different ways we can do this. If we wanted to, we could specify like the angle, which I'm going to do in a bit. I'll show you how to do that. Or if we wanted to like explicitly just say the distance and how far the X travel is, we could do that as well. All that stuff. And then, you know, we'd probably need this one as well. So we'll take that there. So that should be, I believe, all of them that we need for this top part, or at least for our vertical directions. For our horizontal, we'll take this line as our datum. So again, we'll measure off to here. And in this case, we probably don't care as much about this distance, so we can just probably take it from here. And that would be that one. And this, of course, signifies that this distance matters way more to us than this one, at least the distance between these holes. And then the last one we need, of course, is to the, oh, not that one. From here to the center of our circle. So that's that one. You want to tend to kind of organize these in a way where they're kind of, you know, scaling up in a way that makes sense. So this is probably okay as is. I believe everything that needs to have a dimension is dimensioned right now, which is good. Okay, the next thing I'm going to do is I'm going to go to this chamfer dimension. I'm going to measure off this chamfer. So first I'm going to click on the edge that is my chamfer. Then I'm going to click my reference, and there you go. This tells me that I have a 5 millimeter chamfer here. So that's 5 millimeters this way, 5 millimeters this way at 45 degrees. That's all good. I'll add one more here. So we'll click there and then there, and that gives us that one. And that's pretty much all good there. Oh, I lied. There's one more one more big one actually. The fact that we need to know how big these holes are. So that one's 10 millimeters and this one is 60. So that's that. Everything is basically dimensioned. All good there. Just want to give myself a quick sanity check, make sure I have everything. Feel free to call it out Dora style if I missed anything, but I think we're good. I guess technically, if I wanted to be super pedantic about this, I'd want to measure off this way because of how I defined my datum. So this is technically a more correct way to measure this off, though we could get away with the other one if we wanted to. But that should be okay. It looks like everything is good now. So the next thing I'm going to do is I'm going to add in all our tolerances because everything needs to be toleranced.
Here, we've got a question in the chat.
Yes, sorry.
Sorry, it just says, do we need to use a ×4 modifier for the chamfers and the holes, or is it implied?
Yes, so we do have to do that. I was going to get to that in a bit, but actually let me cheat real quick and go up here to my options because these lines are bothering me. I'm just going to go document, properties, documents, chamfer, and I'm going to forget which one of these. I think it's this one. Horizontal, and then diameter. Only thing I'm doing right here is I'm trying to get these to like curve so that it's a little easier to work with. There we go. And I believe, yeah, there we go. It's just a little cleaner to work with. So yes, you're 100% correct. This does need a, there we go. If I just double click on the measurement, I can come and time and write X4 for my 4 times. But first, let me add our tolerance here. Chamfer tolerancing is a little bit weird because you have the angle and the distance. Go ahead and I'll leave that one for later. Same for that chamfer, but I will add the ×4. Same for all of these holes. So these should also have both I'm kind of just assigning these arbitrarily, but there's that, and then also ×4. And this one also needs a tolerance of, we'll also say 0.05. All of these also need their tolerances. What we could do instead is if we wanted to just make a note somewhere down here that specifies, hey, unless specified, assume all tolerances are 0.02 or something like that. That is fair game. So I won't write that down right now explicitly, but we'll go ahead and assume that that's the case. So everything, all of these kind of length measurements, we'll just assume that they're, toleranced off to say like 0.05 or something. So that's that. Cool. The next thing we're going to do now, let's see. Okay, so essentially, let me kind of backstep real quick. Right now, we're good enough for just a simple engineering drawing. Like if we wanted to, hand this off to someone and be like, hey, can you make this part for me? They would likely be able to get everything done for you and be able to take all the basic measurements and all that stuff. And you'd be able to essentially get a functioning prototype part by the end of that process, and they'd have everything here. So before I move on to kind of how we do the feature frame and hopefully clarify some questions on what that exactly means, any questions on this kind of more basic just drawing level stuff of GD&T? Also, if I made a mistake, please feel free to call me out on it. I am kind of speed running this, so it's very likely that I might have made something up.
You have to mention the thickness.
Okay, so this is, it kind of depends. If this is, let's say, like a 10 millimeter stock, we can get away with not specifying it if we just specify down here that our material is 10 millimeters. For this case, I think it's okay if we, oh, nope, not that. I think it's okay if we just mark this off as, nope, why are you refusing to do this? I guess we'll take it there. Mark that off as, I guess that just 5 millimeters should be okay. So yeah, that one kind of just depends on what you're making this out of. So I'll say this was like a bigger piece and we were kind of facing it off before we did everything else. Yeah, we'd need to specify that. Cool. Anything else? Any other questions about this? All right. So let's go ahead and move on to the more complicated stuff. And I'll try to explain this as we go in hopefully a better way than my example, because I know that was kind of a lot. So the first thing we're going to do, we're going to go up here to datum feature, and we're going to mark our datums. So this is going to be my A, this is going to be my B, and then we'll take the top side of this to be my C. Let me just move this just to make some more room for myself. Cool. You can also, if you click on one of these, you can go down here and go to the scale. If you wanted to make it smaller, so we can do this 1 to 5, just so it's a little out of the way. You can also add in write in a custom number there if you so choose. So yeah, here's our datums. All this means is we are asking for all of our measurements to be taken from this side. So all of our horizontal measurements are going to be taken with respect to right here. All of our vertical measurements are going to be taken with respect to B right here, which we've been consistent about, right? We've specified these two are here. I mean, minus this whole example, but we were kind of explicit about that. And then, of course, all of these measurements are taken from down here. This C1, this one would likely correspond to this measurement, but also what we're going to use it for is specifying that kind of greater tolerance on these holes that I was talking about using the feature control frame. That's up here, so we'll go to geometric tolerance. We'll see this little window come up, and sure enough, we have all of our symbols here. So first off, we'll start off with a position tolerance. We'll give it a diameter of, let's say, we said that these were we said that all of these measurements were, we'll say, plus or minus 0.02 or something. I know these numbers don't really make sense, but I'm just kind of going with it. So we'll say we want a diameter tolerance of 0.02. My primary datum is, nope, not that. My primary datum is going to be A, secondary B, tertiary C. And that's now have our feature control frame. It's pointing in the wrong place, though. That should be there. So now what this means, just to kind of go through the example again, this is saying that when we measure this hole, right, we measure it with respect to A and B, and we take these two values and, this value, and I guess it's up here, this value and this value, right, the 200 or the 20 and the 154. And when we measure that off, instead of measuring like a square, so let me pull up the markup real quick. So right, like with the normal measurement, right, if this was say like plus minus 0.05 and say the same for this 20 measurement, that technically means we have this square here, right? That as long as the center of our hole falls into this square, we're okay, right? Does that make sense? That's what this kind of like basic, if we ignored this feature frame, that's kind of what we're saying. What this feature frame is saying instead is, we're saying instead of, hey, take a square, it's saying, hey, at 20 and 154, plus or minus whatever our tolerance is, we're going to put a circle. All right, that's what this circle is. And this circle is going to have a radius of 0.02. And as long as this center axis of our hole is inside of this hole, or inside of this circle that we've defined with this, then we're okay. Does that make more sense? Hopefully that makes more sense. That's kind of how this stuff works. And of course, feel free to like consult. There's a lot of online resources about this kind of stuff.
So doesn't
yes.
that doesn't that contradict the square versus the circle? Just because one's 0.02 and one's 0.05, like what's the significance of that 0.05 as soon as you take the circle and you say it has to be within this circle, which has a smaller tolerance?
Yeah, so that's kind of my bad of, these numbers I'm just kind of making up on the spot, so they're not really making too much sense. But let's say this was like 0.01, that would make more sense because we'd want this number to be bigger. Yeah, so that's my bad. I should be more careful when I assign the numbers. But essentially, you're saying wherever we figure out where the middle of this is, so that would be this square, we're also adding this circle around it and saying as long as it falls within this, we're okay. So this is, like I said, this is more for like mass production stuff. So this is likely not something that you'll do at like the ASME level, but it is useful to know this. I have been asked on a couple of job interviews, for example, and companies definitely like to use proper GD&T than just drawings. But yeah, that's essentially how that works. Hopefully that kind of clears that up.
Another question.
How do you apply C datum? Okay,
Oh, yeah.
yeah. So this C datum specifies my perpendicularity. So what that would mean is if I took, this hole, right, and I'm saying this is the center axis of my hole. If I draw a cylinder of diameter 0.02, and that cylinder is perpendicular to datum C. So that's where this C comes in. Is specifying that I want this cylinder to be perpendicular to this top face. As long as my blue line, which is my central axis of my hole, falls into the cylinder throughout the whole length of the cylinder, or throughout the whole length of the part, I'm okay. So that's why we specify this C. So it's not really too necessary for like thin parts, but let's say you had like, this was like a deeper part, it's very likely that you're probably going to, obviously this is an exaggeration, but you're probably going to get a hole that looks more like this than, straight vertical, just because of like some error in the, let's say, milling or drilling process, however you're making the part. So this C just specifies that, hey, as long as you're like kind of within that area, we'll be okay. So hopefully that clears that one up as well.
Is it normal to put that extra bar of controls that you added on a different hole than the dimension, or would it normally be on the same hole?
Yeah, so that's the last thing I was going to do. So now that we have this, technically what we need to do is I'm going to come here, copy all of this, come over here, and right here, as soon as I click on this, it's going to open this text box. I'm just going to click in front of it, hit enter, and put that right there. I guess I accidentally copied the new line character at the end of it. But essentially, this is the correct one. And since SolidWorks is kind of dumb, I need to change this to 10.0. But this would be the correct way to dimension that. So it would look like this.
Cool.
And then obviously I'd do the same for this big hole. I'd add another feature control frame, copy this part, paste it on top, and all that stuff. Same for the chamfers, but again, they get a little bit more complicated because of how we have to kind of use the other features, and I don't want to confuse people too much. This is more of just like kind of where to find stuff and the basics that are the most important. So yeah, again, this stuff, if this kind of flew over your head, don't worry about it. This is, again, just kind of like an intro to, so that like, if you ever see this, you don't just get completely confused. You can be like, okay, let me open up my ASME handbook and be like, okay, what does this symbol mean? Oh, it means that. What does this? Okay, it means that. I know that this is my tolerance value associated with this, and I know that these are my datums. And then you'll be, you can kind of figure out what exactly is being asked of you. So yeah, hopefully that's that. But realistically, yeah, for ASME, at least like ASME at UCLA student club purposes, something like this is probably more than enough, or not more than enough. This should be the baseline, I should say, because when you're manufacturing stuff like this, there's absolutely no ambiguity. No one's gonna take this part and like send it back to you and be like, hey, how did you want me to like cut off this portion of it, right? That won't happen because you have everything fully defined, and you have it defined in a way where it's like, okay, I got you. You want me to measure from here to here with the caliper, measure from here to here with the caliper, measure the radius of the hole, measure from here to here with the caliper. Like it's all of this is completely laid out in a way where I know exactly what you're asking of me as the manufacturer and as the engineer if I give you the part back after I've made it. So yeah, that's essentially very much crash course GD&T. I'm sorry if it was a lot of information or if I lost anyone, especially with the feature control stuff, because that was just a lot, even for me, and I've seen it, in practice before, and it still kind of trips me up every once in a while. So don't worry about that. If in case I lost anyone, what I'm going to share really quickly is if hopefully this is showing my Chrome right now, or is it still SolidWorks? Can I get a confirmation?
Yeah, we can see the Chrome.
Okay, cool. So yeah, these are this is a really useful website, and there's links to these at the ends of the slides, which are nice. But essentially, all of these symbols are defined. They have these useful examples. So, for example, the position one that I just used, or on this last example, you can see if we click on that, they have a handy video on it. Look, we dimensioned it correctly. We have our tolerance and all that stuff. Any significant differences in ISO and ANSI? They're just two different standards. I don't remember which one the US uses for standard and which one kind of Europe uses for standard. I think ANSI is more commonly used. I see, Jacob, you're unmuting, so maybe you have.
Yeah, it's the A and ANSI is American, and the I and ISO is international.
Okay, yeah, that would make sense.
That does make sense. Yeah, I've used ANSI. They told us to do that in '94 every time we did anything. So,
right.
Yeah.
Cool. Also, I just realized something, and I should have clicked when you asked me earlier about it. But yeah, you're totally correct about when we add the feature frame, we're kind of overriding this dimension, the tolerance for this with that one. So it's not really as necessary, as you can see here, right? So this distance to the hole is 30 and 20, and we're not specifying the tolerance to that because we have this specifically outlined. So that was kind of my bad on that legacy wise. But yeah, so you can see here's the example I was talking about of how kind of this circle fits inside of our explicit hole that we're defining. So for example, here's the one at the C. You can see that as long as we kind of fit within our circle that we're specifying in our feature control frame, then we're okay on the part. So yeah, that's my my knowledge on GD&T. Of course, I'm no expert. I'm merely a graduating senior who's kind of had to play around with this because of internships. But yeah, hopefully I didn't lose anyone. I'm more than happy to answer just any questions for the remainder of the time. Or at least, actually, let me really quickly, I do remember there are some more slides. So let me, I guess, let Rebecca and Matt finish up, and then I'm more than happy to just kind of stick around.
Yeah, thanks so much. I do want to make a really quick note. I realized we forgot to talk about this earlier, but anyone who's here from X1, just to clarify, we don't require like you guys to actually do this when you're writing your technical reports or when you're manufacturing. This is pretty high level stuff. The manufacturing we have access to, we do it all ourselves mostly, and it's not usually this specific, this professional. It takes a long time to do this kind of process, so we're not requiring that, but we just had this workshop because it is a really useful skill for you guys to know. So don't freak out and think you need to be experts at this for your X1 projects or really anything within ASME. All right, yeah. So
if I could just, sorry, but just to like, if I may add one small detail to that is, yeah, definitely like if it's overwhelming for you, it's overwhelming for you, and that's all good. But what's nice about this is, let's say you do have to manufacture something, you don't have to keep looking at the 3D model and like using the measurement tool of SolidWorks. So that is one reason why you might want to consider like doing these out, especially for more complicated stuff. If it's like, okay, cut the PVC pipe at 24 inches, then maybe you're all good. But
yeah, for sure. No, definitely having some kind of engineering drawing is really useful. Yeah, I would recommend that if you've got a complicated part like this. But the specific GD&T stuff we don't usually use. Yeah. All right, really quick to finish out the workshop, here are some links to some useful information if you want to get more info about this. That's the website that John showed is this GD&T Basics one. This is just another article that introduces the basics of it. And then this is the SolidWorks help page that has a lot of specific details about what you can do within SolidWorks. They're usually pretty good. And Matthew?
Yes. Okay. So just a little bit of more info upcoming events. We got Codenames Night next Friday, May 14th. And we got, as I was told, is pronounced Squashy, the Spring Quarter Online Secret Santa. I highly encourage you guys to sign up. I think I'll be doing so as well. We've got the ASME banquet too coming up. That's going to be May 22nd, 6:30 p.m. And again, just on the right side here, you have some contact. If you guys want to contact after this or in regards to any questions or anything, you can reach us at any of these contact means. And we will be available at the X1 email to also answer any questions. So that's all.
All right. And any final questions, comments, concerns, jokes, anything at all? We're just going to hang out. But yeah, if you guys don't have more questions, you're free to go.
How do you decide on tolerance for an actual drawing? So I guess the main thing is you kind of have to consider the functionality of the part. So again, to just go back to that main thing, let's say you had like a 10 millimeter hole and you needed to fit a peg through it. You wouldn't want to make them both 10 millimeters, right? Because then realistically, when you manufacture both the peg and the hole, you're going to get into something where they're not going to quite fit into each other unless you kind of cheat and, you know, freeze one part or heat up the other one and, you know, squeeze it in and press fit it. But what you'd want to do is kind of pay attention to, one, what the manufacturing process is. So if you're telling someone to like cut a piece of wood with a jigsaw, you don't want to give them like a plus or minus 0.1 millimeter tolerance, because that's just not going to happen. You know, the blade of the blade of the jigsaw is like probably 3 millimeters in and of itself. So the chances of you getting that is, you know, just not going to happen. So it depends on, you know, how the part's being made, what bit or I guess attachment of that machine or tool is being used, all that kind of stuff. And of course, like the functionality. So for example, to go back to that hole and peg example, you'd want to realistically probably ask for like a 10.1 plus or minus 0.5 millimeter hole, that fair game. And then your peg would likely be like 10.9 plus or minus 0.5, assuming that both of them are like made, well, the peg made on the lathe and like the hole made on like a drill press, and that should probably be okay. You want, obviously, like you want the tolerance zones to overlap a little bit if you want it to be a tight fit, but you're kind of, it's just kind of on you as the designer to get a number for it that makes sense in the application. I know it's kind of a vague way to answer it, but hopefully that kind of helps.
Anyone else have comments, questions? All right, seems like we've kind of reached the end. You guys are welcome to hang out if you want to chat about anything else.
Yeah, I guess just before you end the recording, sorry again for the information dump. I know it's a lot, but the easiest way to get through GD&T is just to kind of play around with it with yourself, by yourself, until it just kind of makes sense. So feel free to use any of the resources. Feel free to reach out to me if you'd like to, and I'll try to shed light on anything if I can, hopefully in a better way than this video. Teaching GD&T is kind of hard, hence why they don't do it in 94.
Yeah, no, this is great, John. Thanks a million for helping us out with this.
Yeah, of course, my pleasure.
Yeah, thanks.
All right, I'm gonna end the recording.